In this lesson, we are going to learn how to determine the limiting reactant and the excess reactant in a chemical reaction using stoichiometry. Please have your note sheet, calculator, and periodic table handy. You can recognize that a problem is going to be a limiting and excess reactant problem when the amounts, the moles, or masses, the grams, are given for two or more reactants in a chemical reaction. The limiting reactant is the reactant that is going to be consumed or reacted first. This is the reactant that you're going to run out of, and once it's gone, the reaction is over. This limiting reactant amount we will use to determine the theoretical yield in the reaction. The excess reactant or reactants are the reactants that remain after the limiting reactant is consumed. So the limiting reactant will be all used up in the chemical reaction, the reaction will be over, and then the excess reactant, there'll be some of it remaining. So let's take a look at some examples. In example 1, we've got the moles of zinc given and the moles of sulfur given. So we have the moles given for both reactants. So what we're asked to do here is find the limiting reactant, the reactant we're going to run out of first. So I can start my BCA table filling in the appropriate amounts in the before row. Now I have to determine which one of the reactants I'm going to run out of first. We're going to look to the coefficients. Now both coefficients here happen to be 1s. So these reactants react in a 1-to-1 ratio. So this is an easy one. The smaller amount is going to be the one that we run out of first, in this case the zinc. All of the zinc reacts until there is nothing left. So this is our limiting reactant. I'm going to call it LR. And the sulfur is the excess reactant. I'm going to call that ER. You can see that 3.5 moles of the sulfur reacts, and then there are 0.70 moles left over after the reaction is complete. Whereas with the limiting reactant, there are no moles left. Let's look at an example where the reactants do not react in a 1-to-1 ratio. Here in this reaction, the reactants react in a 1-to-6 ratio. We have 0.00526 moles of the phosphorus and 0.00853 moles of the chlorine. We have amounts of each of the reactants, and so we have to determine which is the limiting reactant. So I've started my BCA table. Now I have to find the limiting reactant. This is a little trickier because, again, the reactants react in a 1-to-6 ratio. The last problem was very easy. We just picked a smaller number because they reacted in a 1-to-1 ratio. We can apply that idea here. If we take our mole amount for our chlorine, and divide it by its own coefficient of 6. This is like we're figuring out what the number would be if the coefficient is a 1, and then we can compare it to the other substance which has a coefficient of 1. This is 0.00142. So what we're going to do is we're going to compare this number to this number. This is already a coefficient of 1. And we're going to pick the smaller number. So 0.00142 is smaller than 0.00526. So that makes the chlorine the limiting reactant. All of it will react until nothing is left. And then just to kind of prove that that's the limiting reactant, let's figure out for the excess reactant here what the numbers would be. So it's not going to be the same number for the chlorine and for the phosphorus for the change. So this number right here is not going to be the same as this number right here because the coefficients are different. So we still want to do our stoichiometry. So 0.00853 divided by 6 times 1 is that 0.00142. And when you subtract that, you do get a positive amount of phosphorus left over. So there will be 0.00384 moles of phosphorus left over after the reaction is complete. Here's an example where the coefficients are both different, not ones. So again, in the problem, we've got moles of the C3H6 given and moles of the NO given. So we have to find our limiting reactant. And then we're going to be able to figure out how many moles of nitrogen are produced. So we want to look for the N2 in our final answer. So I can start my BCA table substituting in the mole amounts for each of my reactants. Now I've got to find that limiting reactant. So when they don't react in a 1-to-1 ratio, we just cannot pick the smallest one, or smaller one in this case. And so I'm going to take the number and divide it by its own coefficient. So 6.89 divided by 4, 1.72, and 2.35 divided by 6, 0.392. So I'm going to compare these two numbers. The smaller one is going to be my limiting reactant. So I figured out what the numbers would be if the coefficients were 1 instead of a 4 and a 6, and now I can just compare them and pick the smaller one. So in this case, the 0.392 is a smaller number. That makes this NO, nitrogen monoxide, the limiting reactant. I can also, using stoichiometry, figure out how much of the excess reactant reacts and how much is left over after the reaction is complete. And then I can use my 2.35 moles to figure out how many moles of nitrogen are produced, again using stoichiometry. So 2.35 divided by 6 times 1 is our 0.392 number. And so that is my final answer. 0.392 moles of nitrogen would be produced based on the limiting reactant, not based on the excess reactant. I would like you to try example 4 after you pause this video. Please pause the video now and work out example 4 on your note sheet. When you're ready, you can resume this video and check your answer. Now that you've tried the problem, let's check your work. Notice how the reactants react in a 1-to-3 ratio. We have mole amounts for each reactant, and so we need to find the limiting reactant so we can find out how many moles of ammonia are produced. So for the hydrogen, I took the 0.555, divided it by 3, and I got 0.185. And since the coefficient on the nitrogen was already a 1, I just compared 0.185 to 0.235 and picked the smaller number. So of course that was the 0.185. That makes the hydrogen the limiting reactant, and then that's the number that we use along with stoichiometry to figure out how much excess reactant reacts and how much product is produced. And that is the question. So for how many moles of ammonia are produced, 0.370 moles are produced, and that's our final answer. You maybe noticed that all of these problems started in moles and asked for answers in moles. When you're ready, move on to the next part of this video where we're going to take our problems to the next level, where we deal with grams and molarity. In this example, notice how we have a mass for each reactant given. And then we're asked for the mass of carbon dioxide, a product. So this is a limiting and excess reactant problem. We need to find out if the oxygen or the butane is the limiting reactant, and then use the limiting reactant to find our mass of carbon dioxide. Now remember, when we do our BCA table, we can only use moles. And so we're going to have to do a little bit of work here before we can find the limiting reactant. Each of these masses needs to be converted to moles first. Pause the video here and convert each of these grams to moles. Once you're ready, resume the video. You get 0.593 moles of the butane and 1.41 moles of the oxygen. Make sure for the molar mass of oxygen you used 32 grams per mole because that's O2. Now we have to find the limiting reactant, and we have the coefficients of 2 to 13. So they don't react in a 1-to-1 ratio. So we need to find our limiting reactant by taking the mole amount and dividing it by the coefficient. For the butane, we get 0.297 when we divide the mole amount by 2, and for the oxygen, we get 0.108 when we divide the mole amount by 13. So between those two numbers, the smaller one is the 0.108, so we now know that the oxygen is the limiting reactant. All of that reacts until there is nothing left. Using stoichiometry, I can see that there are 0.376 moles of the butane left over after the reaction is complete. And now I can move on to the carbon dioxide, which is what the question is about. Now this is a coefficient of 8. So it's not going to be 1.41 because those coefficients are different, 13 and 8. So I actually have to use my stoichiometry and figure out what the carbon dioxide would be. 1.41 divided by 13 times 8. And I get 0.868 moles of carbon dioxide. Now unfortunately, one more step is required because we want the mass of carbon dioxide. So we have to do a conversion back to grams. So x grams is to 0.686 moles as 44.01 grams is to 1 mole. And I get 38.2 grams of carbon dioxide as my final answer. In this next example, notice we've got molarity and volume for each of our aqueous solution reactants. So this will be a limiting and excess reactant problem, and we'd like to find the mass of precipitate produced. Now remember, the precipitate is the solid that is produced in the chemical reaction between two aqueous solutions. This problem should be fairly easy because we have 1s for coefficients on each reactant and the product that we are interested in finding. But as always, our BCA table needs to have moles in it, and so we need to pause here, find the moles based on the molarity and the volume of the solution. Remember, volume has to be in liters. So please take a minute, pause the video, and find the moles of each of the reactants. When you're ready, resume the video. So remember, there are 1,000 milliliters in a liter, and so we get 0.0688 moles of calcium nitrate and 0.116 moles of sodium carbonate. Now again, they react in a 1-to-1 ratio, so we just pick the smaller one as our limiting reactant. So you can see we have the limiting reactant reacted until there's nothing left, and we have 0.0472 moles of sodium carbonate left over. That's our excess reactant. And we get 0.0688 moles of calcium carbonate. And unfortunately, we're not done quite yet because we would like the mass of precipitate produced. So from moles back to grams. So 100.09 grams per mole is the molar mass of the calcium carbonate, and we have 6.89 grams of precipitate produced. I would like you to try this final example after pausing the video. When you're ready, resume the video and check your answer. Remember to convert each of the grams to moles, only moles in your BCA table, and then you need to find the limiting reactant. The sulfur ends up being the limiting reactant when we take the mole amount and divide it by its own coefficient, 0.667 versus 1.76 for the aluminum. Now notice the question is mass of excess reactant that remains after the reaction is complete. So this aluminum is our excess reactant, and the amount that remains is this 2.19 moles. That's what's left over or remaining after the reaction is complete. However, we don't want it in moles, we want it in grams. So one final conversion back to grams. And now you have 59.1 grams of aluminum remaining after the reaction is complete. You can always kind of do a double check here and take a look at how much you started with. And this amount left over should be lower than what you started with. So this answer does make sense. After watching this video, you hopefully know now how to determine the limiting and excess reactant in a chemical reaction using stoichiometry. If not, please go back and re-watch this video.